No, I mean, you can, yeah, jobs are there. Yeah, it is right. This is not.
Oh, okay.
This is not.
It's Zoom or something?
No, no, we started live stream. I'll put the speaker muted. Mute பண்ணதுக்கு mute பண்ணிட்டேன் இருந்தாலும் எடுத்துக்கலாம் எடுத்து
How was your village to, how was your trip to village? Nice. Yeah, right. Very. A lot of water. You are taking like continuous classes today here to go IIT. Why? Good. Good for us. No, I'm not sure. The students, I'm not sure. Not sure. Yes. I thought I had left my phone somewhere. We were looking for it. Yeah, yeah. It was in the canteen. Oh. Okay.
We're waiting for somebody to clean the boards.
Okay.
I can clean it, but she didn't want me to do it.
Okay, there's
Then it saves on energy.
I see.
How long do you
Maybe she got it.
No, no. No, you wouldn't, no, you can't stand that.
So 1 hour and then some discussion, right?
1 hour.
Hmm. I hope the rest is shocked.
Oh, yeah, the printer thought I already checked.
Okay,
I also brought.
I see. You bought stocks as well?
I already covered my jobs.
Oh, wow. So those are like dustless stocks?
Some something like that now.
I see.
Okay, not critical.
Yes. Okay, so thank you. Thank you. Okay, so it's my pleasure to welcome all of you to Professor Muthukumar's first lecture. So Professor Muthukumar is no stranger to IMSC. He has visited us quite frequently. He's an authority in the field of polymer physics and statistical physics, and he's right now a professor at the University of Massachusetts in Amherst. So without any further ado, Professor, with all yours. So, politics, that is, you are already heard. Liquid information. That's what I studying. Okay, and we call this VLLPS. Right? And the key question is, can you see this, the back? Or should I write it bigger font? Okay, good. Okay, so too much interest right now, very active interest in this phenomenon. And why is that? If you take a biological cell, right, and there's a cytoplasm, and there's a nucleus, and that's a membrane, and this is a membrane. And there are lots of ion channels, lots of information going back and forth. And here, you know, there's a nucleus, you have all the machinery of RNA coming to the nuclear pore and protein synthesis outside, etc., etc. Now, what is interesting is that in both the nucleus as well as in the cytoplasm, people definitely recognize a plethora of spontaneously formed aggregates. So let me draw something like this. One here, one there, a tiny one here, more there, and inside one, for example. Suppose I have an example here. Suppose I take this to P-body. This is essentially made of an protein called alpha-synuclein. The Parkinson's disease. And if you have inside a nucleolus, for example, and all the functions of the RNA, synthesis of RNA, functions of the RNA, they're all exhibited by this spontaneously aggregated structure. As it turns out, we do not know yet how they are able to function biologically without any membrane. Because here, we have channels, potassium channel, sodium channel going in and out, but here we don't have those channels. But still, they are able to exchange information within the background. Right? It's really remarkable. And when they look at this, they thought, 20 years ago, it's more like an oil dispersed in water. Right? Then, because of that, they thought that this would be liquid-liquid phase separation. With oil in water, is a liquid-liquid phase separation. And that's in the context by which this came about, this nomenclature came about. As we will see later on, it's not going to be as simple as oil and water. All right, we'll explore more. So that's the idea.
Call them aggregates. You deliberately call them aggregates to kind of distinguish from usual liquid-liquid phase separation? Or?
Well, we will see. I do not know. We'll see 2 lectures down whether we should call them aggregates or something else. You know, we'll talk about that. But right now, it's you can call them to a droplet, and whatever droplet, and there will be some structure, right? And in fact, that structure is hierarchical in nature because the objective of this droplets is to provide lots of biological functions. One function, it's a multitude of functions. Therefore, the structures have to be also hierarchical. So it has to be hierarchical in structure, as well as the dynamics is also hierarchical. All right. So it's not simply an oil drop. Okay. So we'll see. So when you take an aggregate, there's also hierarchy, right? So we'll see more about what we know so far. Okay. So the other thing is, if you wait long enough, the bottle is strong, right? Then as it matures, it undergoes a liquid to a solid transition. Like the liquid to solid transition. As a transition. Not a aggregate, but it's not a droplet, right? It's not a large droplet. As it turns out, the phenomenon is humongous. There's a huge interest in the world to figure out how they are formed, how do they mature, and what happens in here. And if we understand this, can we go back and interrupt formation of unwanted aggregates, fibrillization. Perhaps it can have implications in terms of controlling diseases. Okay, so that's the goal. That's why we are interested in this subject.
But what does fibrillation?
Right, it's an object. Once it goes, we will have, as they mature, fibers. And we still do not know how a three-dimensional aggregate or three-dimensional collection of molecules are able to nucleate one-dimensional fiber. We do not know that yet. This is one big challenge today, and many laboratories are working on this. They are experimentally interrogating the initial stage of fibrillization. All right. Now, please feel free to interrupt. Okay, so this is our target. This is what we want to understand. Okay. Perhaps just to tell you this, already I kind of resolved the title of our this local liquid phase separation. That's simple, right? It's not the typical liquid phase separation. But today, we're going to talk about what we know as an honest to God liquid phase separation. I think that's a good basis to have, and then on top of that, we can dress it up with the other details. Okay, that's the way it's target. Now, how do you do this? Suppose I go and look at this body, the orthogonal molecules, RNA, magnesium, other biological molecules. They're all put together. They are many component system with self-assembling into some structure. Right? How do you do this? And in this audience, we know how to do this, right? Let me go and look at one of these molecules here, right? One molecule may look like this one. One molecule. And we're talking about hundreds of molecules of one type, and also hundreds of molecules of two kinds, three kinds, etc. And if you look at this one, it's already quite interesting. Right? So let me put one. Here's the blue charge, blue color is positive charge. So this one, this one, this one. I'm just doing the cartoon. And then negative charges. And then no charge. Hydrophobic, like this. Each one has a sequence. Each one has a sequence, particular sequence, right? And the sequence is not too tight in these systems, unlike folded proteins. We take folded proteins, the sequence is very tight, so they make compactification. The evolution chose those sequences, right? They're able to fold. But here, they are intrinsically disordered. That means it's more like a charged polymer, polyelectrolyte. Because there are sequences where there are more charges of same kind, right? So they are like repel, so they don't allow, this interaction do not allow the molecule to go and flows, right? And that's a very key aspect of the phenomena we are going to talk about. When they are folded, the functionalities will be robust and will be unique. When they are not folding, they are able to undergo tremendous conformational fluctuations to energy landscape, etc. And therefore, the molecule is able to explore possibility of local free energy minima, and hence, in the with the with another molecule or a docking, you can exhibit unique properties of a different kind. Same system can exhibit different functional properties. So that's the attribute of these guys. So I'm going to call this to be IDP, intrinsically disordered protein. Right? Intrinsically disordered protein. Okay, how do you do this? The principle is easy. Right? What to do is the following. So let me take one example, two molecule. I want to know the free energy of one molecule. What do you do? Form over all combinations and then 50. There is no such a thing as a ground state here. Right? That's a big distinction between foldable proteins and IDPs. Right? So it's more like a gassy in that sense. High temperature gassy. All right. And what do? We write Hamiltonian. With the minus the one we're talking about. I'm going to write something like this: 3 by 2 L squared summation over I Ri minus Ri plus 1 minus Ri square. This is connectivity, right? I'm not putting any declaration here. So between one monomer and next monomer, the freaking string and the energy associated with the freaking string can be written like this. Okay. This is the length between two amino acids. Nearest amino acids. Okay. The two dimensional, that's why I write 3. Half, always half has to come because, yeah, it's related to kinetic energy. Anyway, so usually minus 3 over 2L squared or I plus 1 by Ri squared. This is a chain connectivity. Right? And this one is not a fixed conformation. After a picosecond or a nanosecond, this conformation will be somewhat different, but still maintaining the topological connectivity. Now, how do we write the interaction? So we write the interaction as follows: summation over I, summation over J. We will write sigma I, sigma J, and we write V, any interaction, V. But if you want to do it, I will just for the first step. R is a position of the ith monomer, or J is a position of the jth monomer, right? And this is a sequence. The sigma I, sigma J, sigma I, with this one, it could be positively charged, negatively charged, or it could be neutral, or it could be bipolar, it could be quadrupolar, or it could be neutral. Sorry?
What values does sigma take?
Should I like speaks it over coming over I then J? What is the actual?
There's some level. It is positively charged. You say, let's assume you say +1. If it's negatively charged, put -1. For charge, very easy. If it's neutral, put that value is 0. Right? And then if it's 0, then interaction will be somewhat different. So this is kind of able to read the sequence. Okay. So this one, again, put down the ones. Actually, people call what? Hydrophobic. There you go, your dipole-induced attractions, right? Which is responsible for your gas being liquefied into a liquid in lower the temperature. So maybe it could be Van der Waals, particularly for these is the weight ones, that's van der Waals. Then we do charge. If you are the charge, there will be the repulsor. If you are opposite charge, there will be attraction. Then you can have charge a dipole. And the whole list goes on. Dipole, and then the particles, and then the sequence, knowing the chemistry, we prescribe them in here. Then there is a technology by putting this, which is a representation of your particular IDP, your proper representation. Now, accurate representation of your IDP, that goes in here, topological connectivity goes in here, the sequence goes in here. Particularly where they are ordered goes in here, then we use a technology to do the summation over confirmations. We use field theory, right? Or on a computer, you write the algorithms, just run over all possible confirmations, and then from there you get free energy. Once you get the free energy, you can get the size of the molecule, the structure, etc. Right? Then it's not only for this high level, only for one molecule, but many molecules. So we write here summation of I alone, summation of I, and then summation over another one. Say for the first chain and different kind of chain. So you can generalize this formulation for any number of chains, any number of molecules, and salt ions, any components, different lengths, different sequences. The technology, and it's doable. Now, some of us know how to do it. We just do it. If you do this, you get everything about what you want to know. Yeah.
So, to have charge, we need to show charge interaction. For our side, we need to show dipole. In which case, it will show quadrupole interaction.
So we have right? We have and then after we have chelating ones, yeah. And then we do a higher order. This is not recognized in this field. When reading the biology literature on this one, they don't even talk about dipoles. Even charges, they don't talk about it. Right? But before that, we can't do it because this is all existing in water. Within in water, right? And if it's not charged, that is not going to be miscible in water. It will not get into the system. So they have to have charges and dipoles. And the water has a dipole moment. So the dipole interactions are extremely crucial to treat.
I mean, that you even in your previous topics in the mind, but what about quadrupole? Have you seen any experimental signature of quadrupole?
Yes, like hyper interaction, there are lots of beams being like aromatic rings, right? And
we're saying indirect case of it, right? There.
That's probably works, but it's also, right? And again, to figure out the orientations for the public stacking. Right? That's not what we stacking. Yeah. There was a question from the please.
Already this free energy for a single molecule, the molecule is moving in three-dimensional continuous space. So it's not a possible number of configuration infinity effectively. So
it's not very large. It's very large. Yeah, it's computable. Yeah, it is computable. It goes polymer potentially, right? But it's not easy.
but then it's in continuous space. So like each particle can
it's a constraint. The total length of this chain must be fixed, depending upon how many amino acids are in this IDP. All right? Yeah. The intuition is right. One of the remarkable things about Mother Nature, the reason why Mother Nature chose polymer to express life is because the polymer chain can adopt enormous number of conformations without having to pay a penalty. Imagine you have a single rod-like conformation, try to change its conformation, you got to break it. We don't want to break our polymer, right? That's why these polymers are flexible, and because they are able to adapt to lots of conformations. But the point that I'm trying to communicate is that is calculatable. And the technology is there, you know. Okay? Okay, so that's the way we have to do.
Differentiate between two conformations on the basis of free energy.
Right? But already there's not a combination. So these are the system. When I write free energy for system, I'm not writing the. So if you take a folded protein, people must look at free energy of a particular conformation, misfolded or folded, whatever it is. That's not what we are talking about. Right? Here, we take an ensemble average. It's able to fluctuate. It undergoes lots of fluctuations, and then you get the free energy of that system. And then you can also calculate and measure, you know, in that way, what the fluctuations in the conformations are. Okay, right. And but still, free energy is an ensemble average. Okay. Okay, so that's it. This is the conclusion of fourth lecture, all right? And that's the roadmap. So we have to do this, okay? And you have to do it because it is so beautiful. A lot of nice things to do. You know, it opens a very nice. It's a gold mine, and we are only in the early stage of trying to accomplish this mission. And the advantage that we have is that we have paid some price to learn a little bit of biology, only a little bit. Biologists are amazing. They know a lot of information, so we need to really pay a lot of respect to them and learn from their experiments. Please tell us what's the secret, what's going on. And we can bring the methodology, technology, and we can collaborate and then make progress. So without that experimental input from them, these calculations may in the wrong direction. Okay, so let me go to the first aspect of what I want to say today about simplicity. Simplicity is when you take, say, 1, can you see blue from there? Oh, good. Yes, I'm very good at it. Small molecules. Let's not worry about IDPC yet. This is going to be the basis for us to understand, right? And I'm going to mix this with 1, 2 red molecules. Okay, and I get a mixture. Okay, and the question is, why do you mix all the time? Or what conditions they don't like to mix? This is a baby question, right? A very simple question. We need to know the answer to that one. And I'm going to convince you, answering that question is going to give tremendous insight into our problem. Conceptually. Not rigorous mathematics, because that's a very, simple thing. Conceptually, it's going to give us a lot of insight, which I'd like to share. Okay, how do we do this? We do it in the following way. Okay, so what I need to do is I need to calculate the energy of mixing. Delta F. F is my Helmholtz free energy. All right. The pressure I'm not going to talk about. It's not that relevant in general, right? In our systems. Delta Fm, and we're going to have two terms, right? It's energy minus the temperature in entropy, mixing. Okay. The condition for mixing is what? What is the condition? Delta Fm must be less than 0, right? If delta Fm is less than 0, mixing. That's the condition. If not, it's not going to mix. We work it out. So therefore, we need to devise a way of calculating, and that's delta Fm. Okay, let's do this baby calculation. Okay, so let me take to make our life easy to get an insight. Let's take our three-dimensional space into a lattice. And I'm going to do is I'm going to move through this black balls and red balls randomly. So that mix in a random way. So the assumption is a random mixing. There is no correlation. Okay, and as you can imagine, when we talk about polymers, the random mixing of these things is not going to be that possible because there's a correlation, right? But let's try to get some idea about that, just assuming it's a random mix. Okay, so I put randomly here, I don't know, anywhere. However we want to do it. All right, that's good enough, I think. Let's say something like this. Okay. So I'm going to assign some energy for two ways to be together. Energy relational energy, let me call it epsilon 1, 1. Energy of two relates to together, let me call that to be epsilon 2, 2. One red, let me call this to be epsilon 1, 2. Okay. Now the epsilon is a negative quantity. If you go and look at this one, for example, let me take epsilon 1, 2, blue and red, right? So typical of 1, 2 interaction, 1, 2 interaction versus the distance between 1 and 2 in three-dimensional space, that's going to have a shape like this, right? For short distances, it's going to be repulsive. For long distance, there's not going to be interaction. So when I say epsilon 1, 2, this is what I mean by epsilon 1, 2.
This type of graph is already accounting for all type of forces between them.
Well, it will be detailed, right? It will be detailed. Yeah, details. Yeah. These will depend on the specific interactions. Yeah. I'm just taking the simplest system of neutral molecules being mixed here. It will be Van der Waals like, or Lennard-Jones if you like. Right. Okay. Okay, so that's what I mean by epsilon 2, 2. Okay, now let's do the calculation. This assignment, I'm also going to make another assumption. Another assumption will be the size of this blue particle and red particle is the same. Otherwise, the lattice will be distorted, there will be a problem. Right? Another assumption is it's incompressible. There are no empty sites. Okay, so I'm going to say, in addition to this, incompressibility, the system is incompressible, and sizes are the same. Okay. Are we ready to go? Okay, how do we do this? Let's try to calculate our delta Sm. Okay. This is the number of ways I can place those effects. Okay. Since I did the incompressible assumption, what is the total number of sites in the system? And the N1 molecules are blue type, N2 molecules are red type. So total number of sites will be N1 plus N2. Okay. So because of this, total number of sites is equal to N1 plus N2. Okay. That means I'm going to put that N locations, and I'm going to distribute the N1 of one type and N2 of another type. Okay. And that one, number of confirmations, number of realizations would be, let me write omega in the final state, right? Because delta Sm is entropy in the final state minus entropy in the initial state. In the initial state is a pure red and a pure blue, and mixing them together, I'm getting the mixed case. If it's thoroughly mixed, let me calculate entropy. Entropy is Boltzmann constant times the logarithm of number of ways. What is this? That is equal to n0 factorial divided by n1 factorial, n2 factorial, right? Yeah. Peace, yeah. Okay. Anyway, and if that's the case, the entropy in the final state would be Boltzmann constant times the log of omega f and logarithm of these factorials, and we'll use a Stirling approximation because these are very large numbers, right? If you do this, this turns out to be, so SF divided by Boltzmann constant will be equal to, what is it, n0 log n0 minus n0 coming from there, and then negative in the denominator, n1 log n1 plus n1 minus n2 log n2 plus n2. Okay, and then given this, let me define a one fraction of type 1. By 1 is equal to n1 divided by n1 plus n2, right? n1 by n0. And phi 2 obviously is equal to 1 minus phi 1, incompressible system. So I'm going to do very simple arithmetics. I won't do too complicated things. Okay, because it's not necessary. We'll do it in the kitchen. Right. Yeah. All right, so that's the case with this. Now going to be equal to n0, I already told you n1 plus n2. So n0 here, n1, n2 plus n1 plus n2, 0. So go away. That's gone. All right. And here I have n0 is n1 plus n2. I get right. This one is n1 plus n2. I take n1 part and combine with this one. That will give me minus n1 log n1 by n0. Take this n2 part of this, combine with this, then I get negative n2 log n2 divided by n0. So I get then minus n1 log phi 1 minus n2 log, minus n2 log phi 2. That's entropy in the final state. Right? I have a tendency to write fast when I do arithmetics, but if I go fast, please stop me. Right? Ask me. Now let's look at the initial state. Entropy in the initial state. Initial is a pure n1 on n1 sides. The number of ways of putting n1 particles on n1 sides is only 1. The logarithm of 1 is 0. Similarly, putting n2 particles into n2 sides is 1. Logarithm of 1 is 0. So entropy in the initial state for this model is 0. Therefore, delta Sm turns out to be minus n1 log phi 1 minus n2 log phi 2. Okay. Let's look at this one. Phi 1 is a volume fraction. Yeah.
If this n1 sites could be anywhere like n1 and n2 sites, they would be like on the left side or the right side. That's it. So you can
I'm sorry, taking now a spatula of n1, right? So I might have one teaspoon of another one n2, and I mix them together. Now pure n1, I have nothing else except n1.
in this box only, if we 50% like n1 is n by 2 and n2 is also n by 2.
That's not the how we are doing that. The how we are doing is, right? I have a sample of n1, there are lots of them here, right? N1, and I'm mixing this with another sample of, let me say, bigger cube if you want, right? Because I do not know the composition, I can put any composition, right? So I calculate this my initial state is entropy of this system plus entropy of that system, right? And then I next time to make a better sample, that is this one. Okay, so but this is very interesting. Why? Phi1 is less than 1, greater than 0. A logarithm of phi1 is negative. Similarly, logarithm of phi2 is negative. And then a negative sign here. Therefore, delta Sm is positive. Right? Delta Sm positive. Because when you try to mix them, it's good for them to mix based upon entropy. The entropy drives them to mix thoroughly because catastrophe, more disorder. When you mix them, you have more disorder, right? If I having only this one with ordered, more or less ordered system, and when you mix them, it's a disorder. Therefore, entropy goes up. So always the mixing is done by entropic contribution. If you make a droplet, somehow I have to beat it. Yeah, I have to really overwhelm that entropic contribution, and that's what I want to communicate. Let's work it out. How do you get energy, right? Okay, so let's do that. Oh, I made a mistake, right? This is in units of kb, right? In units of kb. Okay, so may I erase this? Is that okay? Yeah. Okay. Okay, how do I do this here? Let me see a better way, right, to erase this. Who wants to do this? Or maybe this may work. No. Would it work? Okay, let's do the energy. How do you do the mixing, right? So I want to have a delta Vm equal to energy in the final state minus energy in the initial state, right? Initial state for the first state component plus energy on the initial state for the second component. Okay, that's what I need to calculate. Now let's do this. Who wants to help me out with the energy in the final state? So this is my final state. I need to figure out how many contacts of, say, 1 and 2 are going to be. How many contacts of 1 and 2, right? Then I know the energy. Okay, so let's look at 1-2 interaction. So EF, please correct if I make a mistake. I'm likely to make a mistake. So epsilon 1-2, that's the energy, times the number of contacts I'm going to make. So I work on this lattice. Let me see. I see something like this, 1. Okay, I pick this one. Then I ask, what is the probability that I'm going to find the number to be red? Right, that's the epsilon 1-2, right? I go to look at one location here, and then I ask myself, as a neighbor, what's the probability I'm going to get red? But in this cartoon, I have 4 directions to go. I can go here, go there, go here, or go here. What's the coordination number of this lattice? In this lattice is 4, but let's not be specific. There's a coordination number Z. Okay. And then I ask myself, what is the probability I'm going to get this one? The probability I'm going to get that one will be a concentration, average concentration of red type. That's phi 2. Not a probability because randomly mixed. And then I'm asking, okay, I just chose this one, I found out that answer, but it's the total energy, right? Then I go to the right, then there are 11 such blue spots. And therefore, this will be times N1. Okay, that's 1-2 type interaction. Now let's try to do 1-1 type interaction. Plus epsilon 1-1. Okay, I go to blue, for example, that one. what is the chance I'm going to see a blue as a neighbor? Okay, the coordination number is 0 again. And that chance is I1. And, right, that's a blue. And then N1. There are so many sites. But there's a catch to this, right? When you calculate one-on-one interaction, you don't want to have double counting. So you'll have Z over 2. Okay. In a similar way, you do for the red, that will be Z over 2, epsilon 2 to N2, I2.
Double counting should be also for the first unit. Like you have 1, 2, and 2, right? Depending on how you're counting. But because you have 1, 2, and 2, 1, that so if that is 1, that is pretty good for counting all the ones for 2 and 2.
No, I would choose one, right? I've chosen one, and then ask how many contacts I have with 2.
Then you should also have contributed like epsilon 2, 1.
I will not do it because of that counting. I will not do it. It will look like I will not do it.
Okay.
Okay.
That's
These are the divided. That's what it
That's all. Yes, that's fine. So, another way to look at the I1. Okay. Okay, now who wants to help me out? So this should be a pure component, right? Epsilon 1, 1. 0 coordination number divided by 2, of course. Only N1. The neighbor is the probability I'm going to find neighbor to the blue is 1 because it's a pure system. Similarly, I2 will be equal to Z over 2 epsilon 2 to N2. Okay. Now let's work it out. Okay. Let me write down here. Let me write this to be Z N0, right? N1 divided by N0, so phi1. N0 times phi1 would be N1, right? Here is N1. N1 by N0 is phi1, right? The N0 phi1, and then I have phi2, and epsilon 1, 2. And in here, I will do the same thing. Plus Z by 2, N0, right? And phi1 square, epsilon 1, 1. Here plus Z over 2, the epsilon, sorry, yeah, Z over 2, N0, phi2 square, epsilon 2, 2. And here EI1 would be, it's very trivial, right? If you do this, U is equal to Z N0 by 2. I'm bringing this V N0 by 2. That's a common factor, V N0 by 2. And then this will be phi1, epsilon 1, 1. And from here, I get a Z N0 by 2. And this will be phi2, epsilon 2, 2. Okay, so magic happens. You know, this is kind of trivial exercise and magic happens. Remember, in writing this, there are 3 interaction energies, epsilon 2, 2, right? Epsilon 1, 1, epsilon 1, 2. Similar to this, there is also interaction energy U, R, for epsilon, say 1, 2, right? It will be another thing like this, and that will be epsilon 1, 1. And similarly, U, R, another number, depending upon, you know, what the chemistry is, and that will be epsilon 2, 2. There are a lot of chemical details which are responsible for this value, that value, this value, this value. So by design, there are 3 interaction energies, right? But now let's calculate this one. So delta EF, delta E, EM is equal to what? Z0 is a common factor. Okay. let me take this out. The first term goes like epsilon 2, 2. Excuse me, epsilon 1, 2. And then I have phi 1, phi 2. Did I get this right? 0 and 0, epsilon 1, 2, phi 1, phi 2. And now let's combine this term with this term, right? The V and 0 is coming out, epsilon 1, 1 by 2, and then phi 1, I have subtract this from the final result, so then I have phi 1 square minus phi 1. What is phi 1 square minus phi 1? Phi 1 square minus phi 1. Minus phi 1 phi 2. Okay? So I have then minus half phi 1 phi 2, epsilon 1, 1. Do the same thing for the other component. Given that we have all the literature on LLPS, I'll tell you, right? This is a very toy model. Let's do this. So what I'm going to do then is, I'm going to rewrite absolutely mean field. Yeah, absolutely mean field. This is what you see in all the papers. This is all the press everywhere. Yeah. Because they don't do the equation that I read on before. Right? They always do a mean field. But this one. This one is a 1920 something like we would call it Bragg-Williams theory for metallic alloys. Exactly solvable model. And this is what people do in polymer field as well. Let me not jump ahead. So let me do this. So what I'm going to do is I'm going to rewrite this to be equal to KBT 10 phi 1 phi 2. And this is fairly great. That's the definition. Where chi, so-called chi parameter, is equal to, I have already written down, that's equal to V by KT, and epsilon 1, 2 minus half epsilon 1, 1 plus epsilon 2, 2. But are the three different contributing factors. It's supposed to be only one parameter, according to this mean field theory. So the relative interaction between one monomer of the polymer, say with the solvent, water, solvent, and then solvent-solvent interaction, monomer-monomer interaction, all those things will conspire to give me only one parameter, chi parameter. Now, this has a combination of both biology and physics. How? The chemical mismatch is given by this square bracket term. Temperature comes in the denominator. So they work together. You have to work together. So I could tune the chi parameter either by playing with temperature or by changing sequence. There was an earlier question about how do you tune phase separation by sequence. This has some information, but I'm going to do more, a little bit more about this one. Okay, so we have delta EM, we have delta SM. So now let's try to put them together. Okay. I don't know which one it is. This one? Okay. So delta Sm had the Boltzmann constant terms that one minus Ts, right? Therefore, the temperature comes here. Therefore, now minus sign, so this should become plus. This should become plus. Since the log of phi1 is negative, this delta Fm is a negative because of entropy. That is due to entropy. This favors mixing, right? Now, other term is we just work it out. That's equal to this K parameter, right? KT. The reason why we wrote it like this is for the KT, I want to get it out. Chi times N0 phi1 phi2. Now you see the big push here. It's always going to be negative. This one, we do not know. Depends on the system. If chi is negative, no problem. They are always going to be mixing. They are not going to be droplets. That's the condition. Right? It can happen like 2 ways. One way is with the sequence. Another way is the temperature. If you jack up the temperature, it will become small, and then it's not going to be that important compared to this one. On the other hand, our ionic strength is appropriate, this could be larger than the value that comes from here, right? And in that case, I will have immiscibility because delta Fm is not negative; it will be positive, right? And we will talk about the consequence of that maybe next lecture, right? Before that, maybe I want to point out one more thing. Okay, so any questions on this one?
This you are getting for the single. You have a and look at the lesser than this. Right.
Let's do it.
And also one. So chi time has temperature. It's not always the same working proportion, right? The temperature will have contributed the energy of the chi time.
Oh, sorry. That's what people do. And that's not a really important question. Well, doesn't have to be that way. And in fact, we need to show, look at what it shows. You know, when we increase the temperature, it will also separate. Yeah. So, all these those things. But you know, but that's okay. That's okay. It means you throw this right, and then you put whatever the temperature becomes for these terms are. You know, input and then make a prediction. For this, you don't have to do computation, you don't have to do measurements. Just imagine, just think about it, because these very profound results. Just think about it, and then you can design in the sequence.
So of course, you have the first which is essentially negative and allowing the next thing, right? So actually, can I design the interactions in such a way so this right diameter essentially becomes very small when it's positive, or even effective becomes 0, right? So then this entropy is always dominating and it is always basically mixing, right? Actually, this kind of things like design the interactions in such a way that you have full control over time.
Yeah, absolutely. That's the way people are able to do this. Yeah. And this is bread and butter. It's such a simple thing that we just do on the board, right? It's such a simple thing, but it's extremely profound.
So that's why I sort of imagine a problem where I'm trying to mix two things and there are also some crowding agents in the solution. Then can I think about some of the lattice sites as being derived and analogous?
Yes. Right. And yeah, yes, indeed. Yeah. So you could do it. You know, you're going to define the expression now. you have, in photo, you have 6 parameters, things like that. Yeah. And this is easy to do. You just paper and pencil. Okay, now the question about polymers, right? So let me go and try to do chemical, which is much more related to ours, which is I take N1 common molecules. Oh, I could do even more generally. N1 molecules, since you notice an RNA, IDP, everything, right? N1 molecules of N, capital N1 repeat units, amino acids or nucleotides, whatever, right? Repeat units. This is one pure component, right? Now, in this particular case, capital N1 is 1. Right now, I'm taking a polymer. And then I mix this with N2 molecules of N2 lipid units. Of course, the chemistry of our first component, second component are different, just like the way we are talking about. Okay? Amino acid. Repeat.
Then how it is defined from this in one of two numbers. Where green molecules, which is in one number. Earlier. But now you are filling
Yes. This is problem. Right? So now, what happens is, what we have to do, right? You want to last it again. You can go and you polymer like this. And one molecule is that many green loops. And similarly, the other one will have 2 dimensions, comes out like this, goes out like this. And then here is 1 unit, another unit, another unit, another unit. Unit means monomer. See, I don't want to use a monomer because in protein, monomer is already a big protein molecule. So that's why I'm using repeat unit. Yeah. Is it okay? Okay, good. So let's do this calculation in field theory. Right? You think that it is very difficult to do. Right? Because the correlation limits so long, to make sure, right, when I make this work and I cannot go back, all those things, right? But the mean field theory is doable. I'm going to show you the answer. I was going to do the derivation, but we can do it later if you want. I'm going to write the answer. The answer is the following. For mixing delta Fm by QD2 I want to apologize for this. Same things. Same power. I do not know. Same power. I don't, I was going to derive it for you to show that's what it is. We're going to do it another time. Yeah. Yeah, randomly mixed. Right? And that means we must interpenetrate. Yeah, so completely random, same approximations, right? Random assumptions. Random mixing, ink possibility, and the sizes of the monomers are the same of both the red and blue type. Right? Okay, so now X has a difference. What is phi 1? Phi 1 is equal to N1, capital N1, divided by N1, capital N1, plus little n2, capital N2. That's the only difference. That's the definition of, that's the volume fraction of type 1, and phi 2 is 1 minus phi 1. Any question? So, I'm going to manipulate the equation to show an very important result, conceptual result. Yeah, no question?
The chains can interpret, then it is like this previous model. I don't see any difference if they can interpret each other. Like here, considering chains, if they are now interpreting, like you can see that in random mixture, you can consider this as blobs.
No, no. I see what you say. No, because is connected with the length of the polymer. It is not in there. There is no capital N1. But because it's the property of the polymer shape upwards, when we see the proof, when we look, you will see how it comes away. Right. And yeah. Okay, so let's see the implication of this one. The implication of this one is, so now the do is I'm going to exist and show you same equation. I'm going to write density. Free energy density. Okay. Free energy density is a delta Fm. Free energy mixing density with the N0. That's the total number of sites. That's equal to N1 of N0 log I1 plus N2 N0 log I2 plus chi phi1 phi2. Right? Chi N0 cancels out. This one is phi1 divided by N1. Phi1 divided by N1 log phi1. Because phi1, I wrote down to me, every N1 times capital N1 divided by N0. So phi1 would be phi1 divided by capital N1. Okay. Similarly, I have
It was like it was it Flody who first tagged this one or
yes. This way. That would be right. Very pretty. Yeah. But we know we are running out of time, right? All Huggins, they were working separately at the same time. That's what we call Flody. I should point out, we've got Flody Huggins theory. Flody Huggins. Okay. This is Flody density. Please notice the difference between the previous formula for this molecular case and the polymer case. There's a big thing that must stick out. Okay, give me the number for capital N1. If you take an IDP, how many amino acids some IDP will have? 200? Say 200. Okay, so N1, capital N1 is like a 200. We talked about last term, the entropy term favoring mixing. But now, when I have a polymer, this N1 comes in the denominator, that kills the contribution of this compared to that term. So, for the case for polymers, entropy mixing is not that important. That's magic. And that already gives an insight about why those things form. Because they are polymers. If you were to chop it, and only have only amino acids alone, you will not have droplets.
Okay, is that the reason why evolution has
Minimum proteins are of considerable size.
Absolutely. Absolutely. Yeah. We are fixed. Okay.
So it's a pretty big more on this thing. Right? So the first part you say now in this case because N1 and N2 is considerably large, so the interpreter is sort of like discontinued. So it's now you have energy dominantly, right? And the sign of pi essentially will determine that the least is possible. So and now the example you started with this everything is right. So kind of it's just
Okay. Lengths, contour lengths, right? When we assume symmetry case where N1 is equal to N2, then we call that to be M. So the molecular weight of one polymer is the same as molecular weight of another polymer, let's say, all right, just to make life easy, all right? And then I will calculate free energy density per molecule. Per molecule. Okay? And that will be what? Per molecule means each molecule has n monomers, n means. When we do this, then I have, right? The one is I have to multiply this equation by n. Right? This is for site for multiple by n. So by n, so I get phi 1 log phi 1. And then do n multiply n plus phi 2 log phi 2. Okay? Plus I multiply n so what I have done, or what the system does is, per molecule, the system becomes amplified, the chi, the chemical mismatch is amplified by the length of the polymer. It's really amazing, right? So they have an intrinsic ability not to mix. Not because they are charged, not because they are, oppositely charged, or it doesn't matter. In general, they have an intrinsic ability not to mix. Okay, so there are two messages. Number one, entropy contribution is reduced by polymerizing. So this is a related to the discussion. Polymerization has used polymerization. This is polymerization to compartmentalize functions, compartmentalize structure and functions. Because you want to have compartments, right? You want to have compartments, and you want to polymerize them. Otherwise, if they are small molecules, they are all like in the ocean, wandering around the ocean, right? And that's not what we want. We want to have compartments. And the principle behind that compartmentalization is kind of buried in these equations, in the simplest level, the crudest level, baby step, right?
I think the other thing is that with this nebulous organisms, so you can dissolve. So you can create the compartments as you need them, but you can also dissolve them, which this flexibility you don't have with like with an embedded bound organism.
And that's a very important. Okay. Stop because there's so much for sure. I don't know, I'm starting with we're going to discuss more.
See more related to aggregation. They can easily, if they have short array sequences, those can be made to aggregate the response. So how like reconcile this with these kind of
The question that we had before. So imagine I have your polymer chain, all right? And I have, so let me something like that. Let's say, imagine I have an organization like this. This part is loaded with entropy, right? And when you have more entropy, it likes to select that state. And this is the game that Mother Nature is playing, right? It's energy and entropy. The conformational entropy is not the translational entropy, right? Conformational entropy of these things are playing a role. So there is always an optimization of a conformational entropy. Therefore, it is important to calculate conformational entropy using the field theory techniques. Well, that's very important. That's what you get by calculating. Because you cannot measure entropy directly. You have to infer it from experiments. Yeah. Any other questions?
So you are ruling out the entropy is the reason for the mixing, right? I mean, because of the entropy work, there will be mixing always. But like we have not taken equivalent volume of the particles. We start taking equivalent volume, we can have something called depletion effects. So their entropy is kind of in the phase separation time. So it leads to
No, we are evaluating. How do we evaluate? This is simply a lattice model. Where by definition, it's equivalent problem. So in every side, equivalent particle. So this equivalent is completely taken care of. Right? But there are other correlations. There was an earlier question, if the long range interactions, then you have to calculate it. Yeah. Depletion forces. You do it. Yeah.
So what I understand is that in last equation, the contribution to the mixing free energy is mostly due to the energy minimization. Like the contribution from the energy difference is much more prominent here. Yeah. But then,
This is what we want. So we were getting stuff.
The point is, right? If you want to design your moving sequence, right? So that it will be miscible or will not be miscible, you use this principle.
polymerization and the mixing are two different physical. Polymerization and mixing both have different physical processes.
No, but I already done this conversation. She did it. And I told the formula and tried to ask how it's going to mix or not. Okay, I'm not going to do a non-equilibrium process of polymerizing and then meanwhile it undergo the phase separation. That's very we do, but that's not what we're talking about here. All right. We take a very different IDP, another IDP or RNA, right? And we mix them together in the milieu and we ask whether we're going to mix or not. Okay, it's very clean question.
Yes, like when chi is goes to 0, we are saying it's mixing. But
They're right. We don't have this term at all. Delta UN is proportional to chi. Right? Because 0, we don't have a game. That's the entropy of mixing, right? That's like a gas at a liquid state. But that's not what real world is about. Because it's all depends. As soon as you put chemistry, it cannot be 0. Unless you go to temperature to be infinity. Because there is no temperature. If you go to temperature to be infinity, then it will be 0. Right? Because of obvious reasons. And then there is no organelles and nothing. Questions? Okay.
Say that maximum number of conformation that is required to take up.
Yeah. We'll talk a little bit about that later on. If you have time, yeah. Yeah. I think we should stop there. Somebody really said. I can have any questions now.
So the next lecture will be on 22nd, 50%, and from 3:30 p.m. onward. Please come.
Oh, yeah.
That should be clear.